Well, thank you, Ron, and thank you, Christine. Christine, I didn't realize that philosophy was catching, but you're waxing philosophical. This is good. Well, our guest today is a very special scientist. Born to a Mexican mother who struggled across the border so he could be born an American citizen a few weeks later. He went on to a bachelor's degree at Berkeley, and then a PhD in astronomy at the University of Wisconsin at Madison 7 years ago, moving to Vanderbilt in 2003. It's ironic that the central focus of his research has been on the birth of stars, for in his short time here at Vanderbilt, he has burst onto the astronomy scene just like a new star in the sky. He's held numerous research scholarships and fellowships, including an NSF Career Award, and he's on various boards of the National Science Foundation. He lectures and publishes widely, including a paper on brown dwarfs. You'll have to explain what they are. They're not something you'd find in your yard in the fall. In a recent issue of Nature, which brought him international attention. In his Theaetetus, Plato has Socrates relate the story of how the philosopher Thales fell into a well while walking, because he was at the same time as walking, he was studying the stars. A slave girl mocked him for being so concerned with what was in the sky that he didn't see what was at his feet. Our guest today is no less absorbed in the stars than Thales, and he's got better equipment. But he seems to have his feet more firmly on the ground, committed as he is not just to his teaching and research, but also to outreach, so as to encourage and interest minority students in astronomy and astrophysics. He co-directs, for example, the Fisk Vanderbilt Master's to PhD Bridge Program, and Fisk's Astronomy and Space Science Training Program, where he's an adjunct professor at Fisk as well as being at Vanderbilt. He also invented the Scopes for Schools program in Nashville, putting telescopes in the hands of teachers who might not otherwise have them for their science projects. It's tempting to ask what relevance astronomy might have to our lives today. Well, there are many answers to that question, starting with trying to understand more deeply the world that we're living in. And I'm sure that Professor Stassun has more answers. But I have a sense that in this time that we're living through, in which glaciers are melting, the climate's heating up and sea levels are rising, we humans are becoming increasingly aware of our connection with large-scale physical forces and processes, and the utter dependence of all terrestrial life, including us, on the energy emitted from our very own star, the Sun. Please welcome our very special guest today, Professor Keivan Stassun, whose talk is entitled "A Star is Born, but How is it Made?"
There's a joke about how many PhDs it takes to learn how to affix a microphone. I'm going to hope the answer in this case is one. Well, good afternoon. As David and I were enjoying the lunch, and by the way, what a wonderful lunch you all provide for these events. I want to thanks to the organizers for the fine food. As David and I were enjoying our lunch just before we came to the room here, we were talking about. It turns out David and I live 2 blocks apart from one another in East Nashville, and we were talking about how one of the really nice things about living in Nashville is a sense of neighborhood and of community, and boy, what a nice way to see that made manifest in this very room to have so many friends and colleagues, a few who I recognize sprinkled around the room, but also just fellow members of this wonderful city that we share, and in this incredibly beautiful and wonderful facility here, this public library where I and my family and my newborn son spend quite a lot of time together. It's a real honor and a pleasure for me to be here today to tell you about some of the work that I enjoy working on with students at Vanderbilt and at Fisk. To get us started, I'd like to do something slightly interactive. I hope you'll indulge me in this. I know that when I attend talks and the speaker wants, audience participation, everybody stand up, wave your hands or whatever, I always sort of groan on the inside, and then I reluctantly stand up and do it. So I'm not going to make you do anything quite like that. But I would like to get us all focusing on our immediate physical surroundings. If you would, please, just take a deep breath. Feel that air entering your lungs and exhaling. If you would, take a look at your hands. There's substance to our bodies. Turns out, as there's oxygen in the air, our bodies are largely carbon. The blood coursing through our veins is based in iron. These elements, what we call the elements, these elemental components of our physical world, which we so take for granted. Everything that constitutes the physical world around us, the chair on which you're sitting, the air that we breathe, the constituents of our bodies, as I just said, all of those elements, it turns out, have their origins in the fiery and violent and incredibly explosive deaths of stars. It's one of my favorite stories in all of science and all of nature, certainly in all of astrophysics, is the intimate relationship between us. It's not just an intimate relationship. The very substance of who we are, of what we are made, is literally star stuff. Of course, we all learn in school that life on Earth would not be possible were it not for the light and heat of the sun. And that, of course, is true, but I think very often we fail to recognize just how intimate that relationship is as well. The light from the sun, of course, not only provides heat for us, otherwise it would be much, much too cold on the Earth's surface for us to live and survive. But when we burn a log in a fire, that intense heat and radiation and energy is sunlight that was once captured in the photosynthesis of that tree, concentrated into the substance of the tree, and then liberated in the campfire. That's just one example. But in our everyday lives all around us, we depend on the life-giving, literally life-giving heat and light from the sun. Now, that's all just as way of introduction to say that stars are important. And understanding not only how stars work, but ultimately where stars come from. How stars are born, how they're made, is one of the central questions that astronomers such as myself are tasked with attempting to understand. And so what I'd like to do today is to spend just a few minutes on three different aspects of the research that we're currently engaging in to understand how stars are made. We've known, astronomers have known for centuries basically, that stars undergo processes of birth and life and death. So we know that stars are born. If we were at a telescope, I could point to you, and I'll show you some pictures, examples of stars in the process of being born. So we know stars are born. We know they live out their lives. We know that they die. But a real detailed physical understanding of the stellar birth process is something that has so far still eluded us. And so we're working very, very hard on that problem. So as I say, I'd like to briefly touch on 3 aspects of studying how stars are born with you today. The first question is, what is it that initiates the process of stellar birth? What I'm showing you in this picture is an image of what we call a stellar nursery. This is a region of gas and dust. You can think of it as a very large cloud of gas and dust floating through our galaxy, through our Milky Way galaxy. This particular stellar nursery, we also call it a nebula. This particular nebula is called the Karina Nebula. And it moves through our Milky Way galaxy. It's at a distance from us of about 3,000 light years, which means that this picture, which was taken pretty recently, we're actually seeing in this picture what was happening in this stellar nursery about 3,000 years ago. Okay. Now, that's pretty recent in astronomical terms. And to give you a sense for just how big, when I say this is a large cloud, to give you a sense of just how large I mean by large, one of the... I actually have a microphone. Can you hear me through this microphone? No. I probably... This is just for the camera. Oh, that's why. Okay. All right. I'll tell you what. I'll give you a sense of just how big this is in just a moment when I have more of a zoom. But this image was taken with the Spitzer Infrared Space Telescope, which orbits Earth and allows us to observe the stars and the universe through infrared light. Now, some of you maybe have some familiarity with infrared light. Your television remote, for example, operates with a little infrared light bulb, and so you can't see that kind of light with your eyes, but it is a form of light just like the kind of light that we do see with our eyes. Normally we associate infrared light with heat. So for example, if you're sitting next to a campfire and you feel the glow, you feel that heat from the campfire, much of that heat that you feel is actually infrared radiation coming from the burning logs. With this kind of telescope, we're able to peer deep into the clouds of gas and dust where stars are formed. And in this Karina Nebula, in this stellar nursery, several thousand stars like the Sun are being born as we speak. And one of the very important insights that has come from this kind of study has been a better understanding of what it is that initiates the process of stellar birth. There's a picture of the Spitzer Space Telescope. It turns out that just off the top edge of that picture is one of the most massive, luminous, intense, and violent stars in our galaxy that we know. That star is called Eta Carina. It is a star that we suspect will explode in a giant supernova explosion, perhaps within some of our lifetimes. It's imminently on the verge of stellar death. And very recently, the Hubble Space Telescope took this picture of it beginning to go through those final death throes as it gets ready to explode in a giant supernova. So coming back to this picture of the Carina Nebula, that massive luminous star, Eta Carina, is just off the top edge. Okay? And now that I've told you that, you can maybe look at this image with a new perspective. You see this structure in the cloud material of the nebula. It's sort of striated. It sort of has these finger-like projections. Those finger-like projections don't just point every which way. They point... Oops. Sorry, I went the wrong way. They point, by and large, up at Eta Carina. It turns out that much like similar sorts of structures that we see on Earth that are the result of erosion by water and wind and other types of weathering forces, the gas and dust in these stellar nurseries can be and is shaped and sculpted by the powerful erosive forces of massive, luminous, intense stars like Eta Carina. And so when we look in detail at what has happened to what was presumably once a more or less uniform cloud of gas and dust that has now been heavily shaped and sculpted, we see these very distinct finger-like projections. And now, to give you that sense of perspective on size that I promised you a moment ago, if you look at any one of these finger-like projections, and you can sort of see them all around, in most cases you'll see at the very tip of that finger-like projection a bright point. That's because it's at the tippy tops of those finger-like projections that new stars are being born. Those are the cocoons of new solar systems. And so, the very tippy top of each one of those finger-like projections is about the size of our solar system. Look at that image again. When we say big in astronomy, we mean really big. Several thousand solar systems are in the process of being born in this place. And it's now very clear through this kind of work that what has been largely responsible for triggering this very, very large episode of stellar birth, thousands of new solar systems being born, what has been directly responsible for sculpting and shaping the environment in which these stars are born, the womb, if you will, in which they're born, is the destructive forces associated with the death of that massive luminous star that I showed you, Eta Carina. And so there's a very intimate and interesting, I think, connection that we're beginning to understand between the violent destructive forces in the cosmos and the creative birthing processes that we associate with the birth of stars. I'm just sort of flipping through a few additional pictures so that you can get a sense of what this stellar nursery looks like. Using the Hubble Space Telescope in concert with the Spitzer Space Telescope, these two telescopes have complementary capabilities because they allow us to study different wavelengths of light. We're able to gain additional insight into this process. And so here's a Hubble Space Telescope image of a different stellar nursery that was taken by my Vanderbilt colleague, Bob Odell. And here again, you see the relationship between the destructive, erosive forces of massive luminous stars and the birth and creation of other stars nearby. Down toward the lower left, you see a couple of stars that are shining very brilliantly. Those are the massive, intense stars. And then surrounding, almost like a little halo, surrounding those bright, luminous stars are what look like little guppies pointing in toward that massive star. Those are new solar systems that we can now directly image and study that have been formed in the immediate vicinity of these massive destructive stars. And here's an artist's rendering in the lower right. In the upper right, those are actual pictures of new solar systems being born in the aftermath of the erosive forces associated with the massive stars in this stellar nursery. So it's clear that destruction and creation go together when it comes to making stars. One of the mysteries that we're still struggling to understand is, along the same lines of destruction and creation, is what was the role of intense X-ray and ultraviolet radiation in the early history of the Earth? As life was evolving on Earth, it turns out, we now understand, the Earth was bathed, completely irradiated by the intense X-ray and ultraviolet radiation that the young sun was emitting. What I'm showing you here is a time-lapse movie of a stellar nursery. Each of the points of light that you see there is a newly born star in this stellar nursery. And this time-lapse movie shows you the X-ray radiation, X-rays, like when you go to the dentist, X-ray radiation being emitted by these infant stars as they're going through the birthing process. Young suns emit immense quantities of harmful to life X-ray and ultraviolet radiation. And moreover, that X-ray radiation that they emit is very eruptive in nature. And so that's what you can sort of see in this image. If you just kind of look around, it's the time-lapse movie is looping every 15 seconds or so. You see the stars sort of popping on and off. Each one of those pops on is an immense eruption of X-ray radiation. And so from studies like this, we now understand, this is relatively a sort of new understanding for us, that when the Earth was first forming around the Sun, and life was first evolving on Earth around the Sun, the amount of X-ray radiation that the Earth was exposed to was far greater than what we're exposed to now. Okay? On a typical day, when you walk around outside, you are exposed to the equivalent of about 3 dental X-rays every year worth of X-ray radiation coming from space. That is to say, really not very much at all. Part of that is because our atmosphere almost completely blocks out any X-ray radiation that otherwise would come in, but the little bit that does trickle in is not too bad. In contrast, when the sun was merely 1 million years old, and the Earth was first taking shape around it, the amount of X-ray radiation that the Earth experienced was the equivalent of about 10,000 dental X-rays every second. If you had 10,000 dental X-rays done to you every second, things would happen. Probably not good things as far as you were concerned. But at a stage of the solar system's evolution, when things were just beginning to bubble and boil and interesting things were beginning to take place on the surface of the Earth, perhaps this infusion of energetic radiation was critical, perhaps absolutely critical, to early mutations, to the kinds of developments that we associate with early evolution of life on Earth. These are interesting ideas and ones that we're just beginning to really grapple with as we understand now the physical environment that the early Earth found itself in around the Sun. The last thing I'd like to share with you about what we're learning about the birth of stars is that, I think for most of us we associate the phrase Mother Nature with a sort of nurturing, warm, life-giving sort of image. But how nurturing is Mother Nature really when it comes to making stars? This is something that we're only recently beginning to understand. In his nice introduction, David mentioned some recent work that I was involved in into brown dwarfs. Brown dwarfs are what astronomers call stars, or rather would-be stars, objects that formed like stars, but that when they emerged from the birth process did not have enough mass and energy to initiate nuclear reactions the way that stars do. And so, in a way, you can think of them as failed or aborted stars. We call them brown dwarfs because aborted stars doesn't sound very nice. Up until recently, we didn't know very much about these failed stars. We didn't know how common they were. We didn't know much about their physical properties. And consequently, it was very difficult to conduct an accurate census of different stellar nurseries to determine how many failed stars are there in comparison to stars that survived the birth process. And so up until recently, it's been very difficult to say How often does the stellar birth process succeed? How often does Mother Nature successfully give birth to a star versus how often does that process fail? Well, this past year we discovered the first ever known system of two brown dwarfs that orbit one another in a binary system. And this was published in the journal Nature, as David mentioned in his introduction. And without going into the mathematical details, suffice it to say that when we have the opportunity to study two stars, or in this case two brown dwarfs, in a binary star system, meaning that they orbit one another, and if we're especially lucky to be able to observe such a binary system such that the two objects periodically eclipse one another as they orbit, then it turns out that from such a system we can measure all of the fundamental physical properties of the two objects. And so for the first time, we were able to measure how much brown dwarfs weigh, how hot are they, how big are they, how brightly do they shine. We were able to measure everything about them. In essence, this system provided a Rosetta Stone for us to be able to look at stellar nurseries and to say with some certainty how many of those little points of light are not actually stars, but are failed stars. And now that we're beginning to do this kind of census, I can tell you the early results suggest that nature is at least as often abortive when it goes to make a star. There are at least as many, and probably more, failed stars than successful stars. This really changes your perspective, I think. For me, it changes my perspective on what it means to be one of these oxygen-breathing, carbon-based life forms on a small planet around a sun. If it's more often than not the case that stellar birth doesn't work out, it gives us some extra appreciation, perhaps, for the fact that we're fortunate enough to be around a star that did work out, and maybe gives us some additional sense of responsibility to care for our planetary home. Those were three aspects of current research into how stars are born. The intimate relationship between destructive erosive forces and stellar birth on the one hand. Questions about intense X-ray and ultraviolet radiation as life was first taking hold on the young Earth around the sun. And the new understanding about how common or not the stellar birth process proceeds successfully. With that, let me just end with a few neat pictures of me and a student at the telescopes that we use at Vanderbilt in the Chilean Andes, and turn it back over to David for questions.
So Keivan just asked me how we did on time, and you got it to exactly 25 minutes. But I wanted to start asking you a bit about time. You know that the sun that we have is finite. That you got on this lovely sunny day. Do you know that we only have another 5 billion years of that? And then it's all over. And I asked Keivan yesterday, when we talk about these stars being born, like how long does it take for them to be born? And I don't know if anyone here has a sort of a guess. I thought, is it like years? Turns out, I think he said it was 100 million years. I mean, well, that's a labor. So I suppose what and then I'm listening to him talking about these phenomena. And you read a bit of the astronomy literature, and you come up with brown dwarfs and black holes and red giants, and there are white holes, I think, too. And he's talking about whether nature is these dying stars are nurturing. He uses words like the womb and guppies. I'm just picking up some of these things. And I guess what I'm interested in here is the way in which, in a wonderful talk like this, what you're doing is bringing home to us, or making semi-intelligible to us, phenomena that are really unthinkable. I mean, you think, well, the sun's only got 5 billion years more. And you said that this thing might explode in our lifetime. I've never heard anything like that from an astronomer. Things that occur in our lifetime, they occur in a few billion years. So I guess my question is, do you reflect on the kind of language you're using to bring all this stuff home to us? And is it, do you really think it's successful? Or is it really, are you just left really at the end of the day with a complete mystery? Is that a fair question?
No, it's not a fair question. This is one of the, as far as I can tell, one of the dirty secrets of astronomy is that, as far as I can tell, it's certainly true for me, and as far as I can tell, I think it's true even of my most senior colleagues, that you never really get your head around a number like 5 billion. I mean, how do you even begin to put that into any kind of context? And I think, as it turns out, one of the necessary skills, therefore, to be an astronomer, or at least to be an astronomer who doesn't just throw their hands up in frustration, is the ability to just kind of put aside the fact that you can never really put into any sort of real human context the time, the size, the weight, the luminosity, any of the quantities that we deal with are on such a scale that you really just can't comprehend in any kind of human terms. And so I think to be a successful astronomer, you at least have to have the ability to not worry about that so much. After a while you get used to talking about these sorts of numbers and manipulating them and using them, and I obviously put credence in them. But gosh, if I spent time anymore worrying about trying to wrap my head around them, I would have driven myself insane long ago.
Well, you turned into a philosopher then. Okay, this is my conversations with the philosophical flavors. I mean, this is what you're in for. I guess my next question goes something like this. I forget who it was. I think it could have been Pascal or one of his friends, but he said something like this, that we can see the stars, but the stars can't see us. Right? And that's not just because we're a long way away and they don't have telescopes. I mean, it's. I guess what I take to be being said there is that you think about the cosmos as this immense, unthinkably large and old, I don't know, place, space, whatever, and we think of it as sort of grand and remarkable and all these beautiful pictures and so on. But in some sense, it may be completely meaningless until humans come along and actually can reflect on and can look at. I mean, you don't even need telescopes. Just look up in the sky and think, my goodness, what's going on here? And before we ask that question, there was no mystery. There was no question. There was no issue at all. I mean, and I guess I'm just puzzled to know whether you ever, wake up at night thinking, this very little speck, these human beings, on this little piece of dust in this extraordinary cosmos is as astonishing a creation as the cosmos itself. I mean, do you see what I'm saying? I mean, we're sort of a different order of reality.
That's right. When I teach my introductory astronomy class at Vanderbilt, and we get into some of these more philosophically flavored conversations, I like to tell my students that that in many ways, and there's a certain conceit, of course, in saying this, but I think it's, if not true, at least fun to think about nonetheless, which is that, in a very real way, we are the universe's attempt to achieve self-consciousness. So far as we know, we are unique in the universe, in that we are, by no means are we unique by virtue of what we're made of, carbon and oxygen and iron, and those things all turn out to be relatively abundantly scattered around the universe. So physically we're not unique, but that we are this collection of carbon and iron and hydrogen atoms bound together that look up and think and wonder and form ideas and love and hate and experience joy and sorrow. What a deep and sobering and powerful thing to think that we are the universe's way of thinking. Carl Sagan said, ideas are what hydrogen atoms turn into given 13.5 billion years of evolution. It's a nice way of saying.
Okay, well, this is the last question is the killer, really. And that is, what, as an astronomer or an astrophysicist, I don't know which you are, what do you do with religious questions? And I want to put the question a little bit more carefully than that. It goes something like this. Do you think astronomy could ever force you outside of science to religious considerations or religious explanations of the universe? And if it, or is it just a personal option? Obviously, different scientists come to their inquiry with their own background assumptions. That's not really what I'm asking. I'm asking whether you or your colleagues, maybe they differ in this way, could ever find things, as it were, out there at the end of the telescope that would sort of force them to conclude, to have some sort of religious awakening. Or are you and your friends mostly perfectly happy just working on a scientific basis? I mean, the obvious question, obviously, is, you're talking about the birth of stars, but then people ask the question, well, where does the whole lot come from? And that doesn't sound like a science question, right? And yet, it's hard not to confront it from time to time.
Yeah.
There's another unfair question.
Yeah, of course it's an unfair question, but let's see. I'll do my best. Maybe I'll try to answer it personally. Well, when my son was born 16 months ago, I had a religious experience, but it's connected with all this in the following way. Obviously, anyone in the room who is a parent or who has experienced or been around something like the experience of the birth of a child, understands the power and the emotion and the love and the hopes and the dreams and everything that goes along with that. But for me, in addition to all those normal things, I remember in the first few days looking at my newborn son and thinking, this is one of those times where maybe it's better not to know so much, but I remember thinking carbon, iron, calcium, that and a lot of sunlight. And look at him. You know, there is something that works in this universe of ours that is more than the sum of those parts. There was an act of creation that was deliberate when my wife and I decided to have a child, and that impulse, that ability, that power to tap into the creative forces that are at work in our universe and that manifest themselves on these grand physical scales, we are also imbued with and can create. We can also destroy, of course. But the birth of my son in that way was for me an opportunity to reflect on the astrophysics and an understanding of what it has taken over the 13.5 billion years of our universe's existence to lead to this life, this thing that we call a life that I held in my hands. And it's something much, 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 much more than the carbon and the calcium and the iron and the sunlight. It is all of those things, and all of those things are necessary and essential, and yet there's something else there. Intelligence, understanding, the ability to form ideas. And so that's all a sort of long way of saying that for me, and I think it's true for many of my colleagues, of course I can only speak for myself, for me, there's always a begging of the question. We can understand that stars are, in a very real way, the furnaces that, the crucibles that forge the elemental stuff of which life and the world around us is made. But we can keep asking the question, well, what about, what made those stars, and what made the stars before those, and what made the galaxies in which the stars are formed, and what made the galaxies? And we can tell this incredibly powerful and coherent story in astrophysics, but ultimately that story comes to an end, or rather a beginning. In the beginning, something happened, right? And the modern story of astrophysics has to stop there. We can push our understanding into the recesses of space and time, and that story has an elegant and beautiful and comprehensive set of physical and mathematical laws that govern it, as far as we understand. But we get to that singularity. We call it the Big Bang in astrophysics. Call it what you will in spiritual religious terms. But there is that beginning. And astrophysics and science will never be able to answer, if you beg the question one more step, who, what, why that initial moment of creation that led to everything else and my baby boy in my arms. Astrophysics can't answer that question. And so for me, and I think for many of us in this business, you either don't ask that final why, who, what question. And I think for some people, legitimately, that's the answer, is to not ask that question. I will tell you, for me personally, I have asked that question. I do ask that question, and I have to think that I don't want to tip my hand too strongly here. I have to think that in the initial instance, at least, creation is not accidental.
Okay, we're going to collect a few questions from the audience. Do we have a roaming microphone? Can you bring the mic down the front here? Okay, we'll start out with the lady who's standing up.
Thank you, first of all, for a wonderful lesson.
Okay.
I was absolutely fascinated by the story of how stars are made. But something you said very early in your talk intrigued me also. You said many stars actually die. And I wonder if we know, is that in some way some form of sublimation, or is that perhaps a collision of one star with another, or is there something else in addition to perhaps the birthing process that failed?
Thank you. Okay, next question. The lady here.
I just learned recently that the evening star and the morning star are the same star, and it's the only star that doesn't go with the solar system that everything else goes by from east to west. It goes from west to east. Is there any explanation about that?
Thank you. Yes?
In the Big Bang model, what's the Adam and Eve made up? Was it a chemical soup, or do we have any idea what that would be in that model?
When I studied astronomy 100 years ago, I had to walk from college to the observatory where I lived, and I saw the sky. And I asked the question, when I consider the stars and the things that are created, what is man that thou art mindful of me? So the question is, do you see God looking at you?
Okay, can you pass it down here? We've got another question on the front row.
In science fiction, two of the most popular subjects are wormholes and black holes. Could you comment on what is really known about these?
Okay. The lady in the front here.
In Ada, Karina, you showed these fingers all pointing that direction, and I didn't know whether you meant there was some plasma or some gases out there that were causing the force to go in that direction. But I remembered that when I was a child, I'm 75 years old. When I was a child, we had a churn that was about 2.5 feet high, and we had a stick, and on the bottom of the stick was a cross, and you put a warm, clabbered whole milk in that churn, and you dashed it up and down with that stick up and down like that, and all of the little butter fat that we couldn't see with the naked eye would all get it bigger and bigger and bigger, but they'd all go toward the center with this clump of butter, and when it got a big clump, you knew you were through churning your milk, and that was a force, and I understand all that, but do you have some kind of plasma or something out there that makes those fingers head toward it? Ada, Karina? What was that up there making your... I didn't see a churn dash.
I'm going to ask a rather mundane question. The Earth, when it was formed, was quite hot. Where did all this water come from?
Recently...
Just give him one second. Are you all right? All right.
Recently, individuals like you have discovered several planets rotating around these stars. None yet have been discovered that are Earth-like. What do you believe is the probability, and when do you think we'll find an Earth-like planet somewhere?
How many have you got now? That sounds about like 7 or 8. Is that enough for a meal, or?
Sure. We have about 10 minutes left. Is that right?
Okay, one more question to this lady here, then we will give it back to you.
I'd like to know if there's any time that the public can go out there to the observatory and look.
Let me actually start with that very last one, because I would be remiss if I did not put in an advertisement for the excellent public programming that the Dyer Observatory conducts regularly. So the answer is yes, there are opportunities at Dyer Observatory, about 20 minutes just outside Nashville. You can look it up on the Vanderbilt website. Dyer Observatory is the name, and it's Vanderbilt's historic astronomical research facility. We don't use it for our research anymore. It's now really just a beautiful place for public outreach and for teaching and education. And they have a hotline that you can call to find out what public events are going on. But there are several events going on every month. So please take advantage of that. Let me. One of the first questions was asking about the stellar death process, which I referred to but really didn't go into in any detail. And the question was, in essence, how does the stellar death occur, and what triggers that? Actually, the stellar death side of things we understand reasonably well, and the reason is that over the last several decades we've had opportunity to see, as they occur, these supernova explosions that result from a massive star's death. We've been able to witness that hundreds of times over. So we now have a pretty good understanding of how that occurs, and the basic answer is that deep in the core of a star like the Sun, there are nuclear reactions going on that fuse lighter elements like hydrogen and helium into heavier elements. That's the process by which heavier elements like carbon and calcium and iron are produced, and that then get expelled when the star dies. Eventually, by eventually we mean billions of years, but eventually the raw material, if you will, at the core of the star that the star is using to fuse, to generate heat and energy, that raw material gets used up. And it's at that point that stellar death occurs. So that's the basic answer on stellar death. But we do understand that process reasonably well, I would say. Wormholes and black holes. That's true. These are some of the most popular questions that I think astronomers get. Wormholes are, I would say at this point, basically a science fiction idea. I mean, it's a neat idea, and there's some mathematical basis for them. But we have nothing even resembling, observation or confirmation or even a suspicion that such a thing actually exists. Black holes, on the other hand, are no less, in my mind, fantastical. Black holes are places in space where all of the mass of a massive star, and many times it can be many, many massive stars, amounting to millions of times the mass of the Sun, all of that mass has been compressed into a single point. And so a black hole, one way of describing it physically is it's a place where you have lots of mass with infinite density and zero size. The mathematics of these things are very, very strange. But in fact, black holes are really quite well understood, and there's now pretty solid evidence that a number of black holes have been discovered in our own galaxy and numerous other galaxies as well. So black holes, I would say, are real. We observe them, we study them, we understand the physics of them quite well. The question about the fingers and Karina and sort of what if I understood your question, it was basically what is it if it's not the churn? What is it that's pushing on the material to sculpt and do the shaping of the fingers? So I referred to the erosive sculpting forces of the Eta Carina star, but I didn't really say what was exerting that force. And the answer is that massive stars like Eta Carina shine brilliantly in energetic light like X-rays and ultraviolet light. That energetic radiation actually exerts a pressure kind of force on the material around it. In addition, those massive stars have what we call stellar winds. They exude streams of material off of their surfaces in a steady, rapid stream. And it's sort of like a stream of water flowing through. Eventually, given enough time, it carves out a deep canyon. Similarly, these winds or streams of materials blowing off of massive stars like Eta Carina sculpt and shape and erode the clouds of gas and dust surrounding them. So that's basically what causes those finger-like structures that you saw. Let's see. Maybe I have time for just one or two more. Question about the discovery of planets around other stars. In my mind, the fact that we have now, in the last 5 to 10 years, definitively discovered, we're up to about 250 now, planets around other stars like the Sun, is one of the most important scientific discoveries of our time. We can now say, I mean, for most of human existence, there's been the question, how unique is the Earth? How unique is our solar system? Well, we at least now know that our solar system has hundreds of other ones like it just in our solar neighborhood. In other words, we've only done this kind of study in the immediate vicinity of our sun, of our solar system. We have not yet found, and this was the question, we have not yet found any examples of planets around these other stars that are like the Earth. That is to say, small, rocky bodies. All of the planets that we've found so far are more like Jupiter, big, gaseous, giant planets. The reason for that really just has to do with the sensitivity that we've been able to achieve so far with these techniques. We've not yet been able to achieve the very, very high sensitivity that you would need to find a wimpy little speck of dust like the Earth around a star like the Sun. But we're getting there, and every year the planets that are found are closer and closer and closer to planets like the Earth. And so I think it's inevitable that certainly in the next decade, you will read in the New York Times science section about the discovery of the first Earth-like planet around another star. What a tremendous thing to witness in our lifetimes. And one of the plans that's on the horizon to study these planets, these exoplanets as they're called, is NASA is planning a series of space missions that will allow us to eventually directly image, that is to say, take a picture directly of some of these planets around these other stars, and to begin to study the chemical composition of their atmospheres. And so there was another question about where did the water on Earth come from. I don't have time for that, but related to that question, one of the goals of these missions will be to see if we can find signatures of water in the atmosphere of another Earth-like planet around another Sun-like star. Wow, what times we live in. And I appreciate that this is a conversation with a philosophical flavor, but sometimes it really is just exhilarating to be able to go beyond philosophy and actually be able to see other worlds, study other worlds, not just contemplate them.
That was a very philosophical remark.
I'm an empiricist.
I think we should thank our speaker today. And in the interest of keeping this planet clean, do use the recycling facilities. I think that means you've got to maybe take your box apart a little bit and put the bits in the labeled containers.